तर অলপ নেট ঢিলা আছে।
Hello, welcome to post-contest discussion of AtCoder beginner contest 302. I will explain A, B, C, D, and C will explain E, F. Okay. So starting with A, question is, there is an enemy with stamina A. Every time you attack the enemy, its stamina reduces by B. So basically what is happening, if I have stamina 4 and if A equal to 4 and B equal to 2, at each attack, stamina is reducing by 2. A is reducing by 2. So at first attack, 4 will become 2, and second attack it will become 0. Okay, we have to do this until stamina reduces to 0 or less. Okay, for 5 and 2, we can do this 5 minus 2, then 3 minus 2, then again 1 minus 2. So this is basically division. Number of steps will be 5 by 3, 5 by 2. Okay, so the answer will be is if it is divisible, it will be A by B, direct divide. Else take the CL value of the result. Then for the question B, okay. I'm not reading the whole question. The summary is that we are given a grid of strings. This is a grid. We have to find the string snuke, SNUK, in this grid. It will be either horizontal or vertical और diagonally. इन दोनों में से कोई एक होगा, जैसे कि इसमें ये है SNUK, इसमें SNUK diagonally है, and then इसमें भी या इसमें SNUK 9,3, हाँ ये रहा स्नैप vertically. So what we'll do is just brute force implement. We'll just look at the code. This is a mess, but we'll get. First, I'm iterating through the whole grid. This to do is to iterate through the whole grid. This is condition if I plus 4 is less than n. I'm searching for whole string, so I have to go to I plus 4 index horizontally. I'm searching in this set. This side. Okay, S is here, and S is here, and E is here. S is here, and E is here. Okay, if we start here, I will go to I plus 4. If I is S, I plus 1 is N, I plus 2 is U, I plus 2. That's all. Then I'm searching horizontally, like this. S is here and E is here. Then I am searching diagonally, like this. S is here and E is here. Then diagonally, but this direction. Then again diagonally, this direction, and again this direction. So this 4 direction, this I'll be searching through this one, and this one. So there will be 8 direction. I'll be searching. There will be 8 conditions. Just implement it, and answer is ready. Okay. So So that was all for B. Now going to C. Okay. uh, we are given strings s1, s2, and sn, each of length m, consisting of lowercase English letter, and si are pairwise distinct. It is saying that these strings are pairwise distinct, and we have to arrange these strings in an order such that every two consecutive strings differ by only one letter. That is, if we change one letter from a string, like we can make it equal. So that means that the consecutive strings differ by only one letter. We have to make it like this, arrange it like that. Like if we arrange these four strings by like this, we will get like A, B, C, D, and A, D, E, D. These two strings differ by one character C and E. Okay, this string and this string differ by one character A and B. This and this string differ by one character B and F. One thing to notice in this question is the value of n is very less. This is n equal to 8. Okay, so we can just brute force through it. Like, uh, how can we check like if this is a valid? If we can arrange it in a order such that the consecutive strings differ by only one letter. Like we can generate like all the permutations like sequences and check if that one is valid. There will be n factorial sequences, n factorial sequences. So maximum will be 8 factorial equal to 40,000, and 40,000 is like doable because clearly at 1.8 this is very less than 1.8. Okay, okay, what we'll do is we'll just try out every sequence. Like in C++, we can generate this by next permutation function. We can generate all the permutations of this factor. Okay, these four strings, arranging in every possible order. Okay, we'll arrange it in every possible order and check if it is valid or not. The code will look like this. Sorry. Okay. This function is checking if the string is valid or not. Like I'm taking the first string and I'm checking with the next string. If uh, they differ by one character, then it is okay. If they did differ more or less than one character, that is not okay. That permutation is not valid. And then we are generating all the permutations, okay, and checking it is valid or not. Okay. If valid, the permutation valid, because other thing is otherwise not. And that's for C. Go to D now. So easy questions, not spending too much time. Okay, this is also pretty standard question. Okay, Takahashi has decided to give one gift to Aoki and one gift to Snook. There are n candidates for gifts. For Aoki, their values are this, and for Snook, their values are this. We have to choose two values from A1, one value from A1 and one value from B2, such that their differences, absolute differences, are less than equal to D, and the sum should be maximum possible. So what happens for this array? If we look at it, uh, the size of this array is 2, and the size of this array is 3, and the D is 2. Okay, so we can choose here 3 and 5. they differ by 2 and the sum is 8. If we pick 3 and other value like 15, the difference will be 12, that is not less than or equal to 2. And we take, if you take 10 and 5 or 2 other combinations, the difference will be always greater than 2. So the most appropriate answer will be 3 and 5. Here the difference should be 0, but there are no equal elements here and here, so there is no possible combination for gifts. So answer will be minus. For this one, we'll select this. Yes, it's pretty easy. Okay. Now what we'll do is we'll iterate through each element of this array and try to find out if there exists a, a element like this is array AI A1 A2. We'll check if there exists A1 plus D, like A1 plus D in the array. Like if we found out there exists an A1 plus D, the answer will be simply like A1 plus D or less A1 minus D. If we found an element between this, that's the answer. That will be an accurate like perfect combination. We can sum those values. So what we'll do is sort this array, put array, and for each element in this array, will binary search its like corresponding value in this array, for upper bound, or you can use lower bound. The code will look like this. Okay, the documentation is not that good. What I'm doing is I'm entering to the first array and I'm searching for AI plus D in the second array. AI plus D, if there is element less. So what I'm doing is if this is greater than IT plus D, the difference is more, then that is not a valid. That will be not a valid choice. So we'll just decrease the index. Then I'll check if this is a valid index, and if this is a valid combination, if this is a valid index, the combination will be valid, and I can take the maximum of those turns. And second time, what I'm doing is I'm checking for A1 plus D. I missed A1 minus D. I will check for it. I'm doing the opposite here. Like rather than searching for A1 minus D, I am searching for B1 plus D in the array, in array A. I am searching for B1 plus D. Okay, I am iterating through whole array B and searching for B plus D in the array A. And this, if this combination is valid, I'm taking the maximum answer, and at plus I'm putting it. I put answer equal to -1 here. If there is no valid answer, this condition will not be satisfied, and this answer will be remain -1, and that is the correct answer. Okay, this is whole ABCD. C will explain E and F.
Is my screen visible?
Yes.
Okay. So let's start with question number E. What we are given is there is an undirected graph with n vertices 1 through n, initially with 0 edges, and given there are q queries, there are two types of queries. The first type of queries is joining the vertex u and v, and the second type of query is removing all the edge vertex v has have. So we have two types of query. First is one uv, so that is basically joining the vertex u and vertex v, and the second is 2 and u, where it means is suppose u is u has an edge with these edges. So what we have to do is remove all the edges between them and isolate u. So basically these two are the types of queries. Since what we can do is in this question is like in generally what we do in an undirected graph, we keep an adjacency list or something. So what we can do here is keep an adjacency set and insert the adjacent elements by the insert function of a set, which takes log n time. And while removing, we can just iterate through all the edges currently the vertex f and remove them side by side. So basically that is a simple solution. It's nothing too complicated. Suppose let's run through this example. So what here is given initially, we are given first query is 1 1 comma 2, 1 1 comma 2. 1 1 comma 2 will do is join vertices 1 and 2. So and yeah, at the same time what we have to do is print the number of vertices that are not connected to any other vertex by an edge per query. Like when we process one query, then with that only we have to output the number of vertices that are not connected to any vertices by an edge. So let's run through this example. So first query is joining 1 and 2, and then 3 is alone. So our output is 1. So that's why here it is 1. Then next is our 1 1 3. So we are joining 1 1 3. Now we have 0 vertices which are not connected by any edge. Next is 2 3. 2 3 joining doesn't change anything, it's still 0. Next is we have to isolate vertex 1. So while isolating vertex 1, what we do is remove all the edges with 1. So removing all the edge with 1 will lead us to like generation of one vertex which is not connected by any vertices. So that's why the answer becomes 1 again. Then what we do is again join 1 and 2. So again the answer becomes 0. Then we isolate 2. When we isolate 2, what we can see is 1 2 3, all of them becomes isolated. So that's why it becomes 3, and then we again join 1 comma 2. So the isolated vertex becomes 1. So for this question, what our solution is mainly, initially I thought of DSU, but what we can do is use set for this because set insert functions and erase functions are log n, so we can easily solve it by this. So what I am doing is at first we are keeping a adjacency set which will keep the like adjacent vertices of that particular vertex, and then we are also keeping a set for free vertices. So initially 1 to n, all the vertices are free. So free dot insert I. Then we will process the queries in such a way that if query 1, then what we will do is insert an edge for u, because for u also there is inserting a vertex, and for v also we are inserting a vertex, we are inserting an edge. So for both of them we are inserting, and because u is not like initially suppose u was free and v was also free, then we insert an edge. So u and v are not free now, they are connected by each other. So we have to erase u and v from the set. And one more advantage of set is, suppose u was initially connected with some other vertices, still we can erase u, which won't change anything. So this is how we will process the query type 1. And for query type 2, what we will do is, suppose u is here and it's joined with vertex 1 2 3. So we know in the use adjacency list there is 1 2 3. So we will iterate through the adjacency set and then erase for each vertex adjacent to u, and we will delete u from the adjacency set. So basically from 1 we had suppose u and 2, suppose, so we will delete u. For 2 also we have suppose u and 3, we will delete u, and 3 also same. But what we have to check here is, suppose like our u is joined with 1, and when we erase this edge, what can happen is like this can become a free edge. When this becomes an free edge, then we have to insert again the adjacent element to the free set. We have to keep this in mind, otherwise the solution won't match. And like that we can just erase everything, and at last when like what you had in adjacent set, we have to erase the whole. So we'll just clear it and then free dot insert cube, and at the end of each queries we will just output free dot size. So basically that's it. It's not a very difficult question, just we have to be clever about the data structures we use, and it will fit in the time limit, so we can solve it easily. So that is question E. uh, Now question F. In question F, what we are given is, we are given n sets which will consist numbers between 1 and m, and each set is like of ai size, and what we have to do is we have to make a set. We have to make a set by taking union of other sets such that our final set will have 1 and m. It doesn't matter what is the other, what other elements are in that set. We just need that 1 and m is in that set. And union is like, suppose we have a set with 1 comma 2 comma 3, and we have a union, we do it union with set comma 3 comma 4 comma 5. So what this union will give us is 1 comma 2 comma 3 comma 4 comma 5. So what happens is any element which exists in either of the set will exist in our union set. So what our logic here is, what we can think as the numbers, like the m numbers as vertices, and the sets as like some type of transition. So let's try to understand this with this example. So what we are given is, first of all we will index the sets with 1 to 3 only. Let's use 1 hash, 2 hash, 3 hash and 4 hash. So what we will do is we will make a some type of graph which will look like, suppose 1 hash is connected with 1, 3 and 5. Then 2 hash is connected with 1. 2 hash is also connected with 2. And then 3 hash is connected with 2, 4 and 7. And then 4 hash is connected with, 4 hash will be connected with 4, 7, 6 and 8. And I guess that's all. Yeah, seems so. So what our logic is here is, we will initially start with our starting vertex will be 1. Starting vertex will be 1, and what we want is vertex 8 and vertex 1 exist in the same set. Okay, vertex 1 and vertex 8. So our logic here is like combining sets. Okay, combining sets in the sense, like suppose what we will do is basically our, in short, in summary, we will just do an BFS from 1, and we will try to reach m, and the shortest distance will be our solution. So basically how we will do so. So when we are at 1, what we can see is we are here at 1. So to transition to another vertex, what we have to do is transition through the sets. So how we will transition through the sets? So initially we are at 1. So we will go to its set, which is 1 hash. And 1 hash, in 1 hash we will go to 3 and 5. So these are a same step, going to the set, and moving to any other numbers, any other vertex is in the same, like same category. So first we, from 1 to, we go to 1 hash, then we go to 3, then we go to 5, and 3 and 5 doesn't lead us anywhere. So there is nothing in 1 hash. We will come back, then we will go to 2, then we will go to 2. When we go to 2, we will go to 2 hash. Why we will go to 2 hash? Because we can see 1 is also connected with the second set. So in the second set, what are connected? 1 and 2 are connected. We can go to 1, which won't help us because we already came from there. So what we can do is we can go to 2. We can go to 2, And then what we see is from 2 we can either go to 2 hash or we can go to she hash. So let's move ahead to she hash. Then we move to she hash. In she hash, from she hash we can move to 4 or we can move to 7 or we can move to 2. We won't go back to its parent edge, parent vertex. So we will either move to 4 or we will move to 7. So let's move to 4. So when we move to 4, we can see its parent set. There are two parent set. We can go to she hash or it can go to 4 hash. So we can directly go to 4 hash, and then from 4 hash we can directly go to 8. So by this our traversal will look somewhat like this, from 1 to then 2 to this part. So what we can ignore is 1 to, then this is a same thing, then here and then here and then here. So what we are doing here is like this our second 2 hash set. There is the 2 hash set. We are merging it with the she hash set. Where we are doing this, this 1 2 hash, like this whole is a single step union. Then by this union we can directly move to 4, and from 4 we can move to 4 hash. So basically what we are doing, 2 union she hash, which will cause us to 1247, and then this union 4 hash, which will do us 1 2 4 6 7 8. So we can say 1 and 8 is here. So basically that's just solution. So what we are doing, once I will show here also, so it's easy. From here we will start with 1. We can move to this index and traverse here, or what we can do is we can come to this set, because here 1 is also here, and traverse here. So if we move to this set, she and 5, it won't help because she and 5 is not present in any other. It won't lead us to 8. So we won't move here. So what we will do, we will move to this set and then we will traverse here. Here there is 2. So what we can do is from 2 we can go here, go to the third she has set. In she has set, what we can do is traverse here 2 comma 4 comma 7, and from here we can either take 4 or take 7, doesn't matter. From 4 we can come here, and from 4 we can come here to 8. So this is our final, and how we will start from here. So what we are doing, we are merging this three sets, so taking 2 operations. So what the code will look like for this, we will do some type of BFS, not exactly a BFS, but some type of BFS. So we will keep a graph. This will be our graph, which will basically what we have to notice is there are 2 types of vertices. Mainly the one is the index of the set and the another is the vertex. Okay, so our graph will be a directed graph. Directed in the sense it will move from the numbers to the indexes of the set. This I is the index of the set, and this is our number. This is a directed graph, mind that. And with that, when we come to this set of index, what we can do is traverse through the grid, which we are keeping it here. We can traverse through the grid and then move to other indexes. Okay, so initially what we will do is we want to find the minimum distance. So here it will be we will keep a distance vector and then visited vector. Then we will use a queue for standard BFS. Then what we will do, initially we'll start with 1. Like the standard BFS, we will take 1, and then we will instead of the standard BFS moving directly to the adjacent vertex, we can't do that because here our vertices are not directly connected. Our vertices are connected like this. We will, from our vertex 1, we will move to a set, and from this set we can move to some vertex. So basically the distance from this is 1 only. So that is the main thing. Like if I try to show you like from above, what we can do is move from vertex, we will move to a set. This set will lead us to another vertices. This will suppose take to another set, this will take to another set, this will take to another set. They might lead to the same set also, and this will move to another vertex, this will move to another vertex, this will move to another vertex. So what the thing is, this is one step, this is second step, and like that we are moving. Basically from the vertex we are moving to a set. In the set we are iterating through the vertex, and from that we are moving to that vertex, and from that another set, like that. So what is happening here? Here it is our this is our vertex, x is our vertex. Then we are moving to it, which is our set index. And then in it, we are iterating through the grid, basically where we are storing the numbers. And in that grid, this is again our vertex. So what we are doing, this is vertex, this is ID of the this is ID of the set. Wait, this is our vertex, this is our ID of set, and this is again vertex. So this is our transition. Instead of directly moving from vertex to vertex, there is a mid transition here that is just moving through the set. And then in the vertex, we will just check if distance is -1, that is basically it means if it is not visited, then we will directly, because it is a tree sort of thing, so we will directly move to distance it1 is equal to distance x. This is our first vertex, this x vertex, and plus add 1, and then we will push q like a standard BFS. Then here we will check if distance of m, like moving to m, here it will contain the shortest path only. If distance to m is -1, which we initialize it with here, that means the vertex is not visited yet. So, since the vertex is not visited, that means the answer is -1, and directly we can output answer -1. And if it is not -1, then we will simply subtract 1 and output the answer. That is our solution for question number F. Basically, this thing is the main thing. Normal BFS question, just with the transition is quite different. So now we will move to question number X. So in question number X, what we are given is, again there is a tree with n vertices. There is like let me show you. There is a tree with n vertices. Like suppose this is a tree, suppose small tree, and there is an undirected edge between ui and vi. So basically it is an undirected tree, and vertex I has a ball ai and another ball bi. So there is a ball ai and there is another ball bi. Here another is a2, b2, and like that a3 and b3. So what we do is, like, consider traveling from vertex 1 to vertex v on the shortest path. So this is suppose vertex 1, this is vertex 2, this is vertex 3. So from vertex 1 we will move to vertex 3 and including vertex 1 and n. Like we will include vertex 1 and n, 1 and v, and we will pick up one ball from there, and what we have to find out is the maximum number of distinct integers on that picked up ball. So that is it. So basically initially we are at vertex 1, we can either pick up a1 or we can pick up b1, and then we will come to vertex 3. There we can pick up a3 or b3. So suppose let's consider something like this. A1 is suppose let's consider like this. Wait. A1 is 3 and B1 is 2, and then we will move to another vertex where A1 is 2 and B1 is also 2. So what we can do here is, suppose this is vertex 1, this is vertex 2. So first we pick up 3 here, and then we have to pick up 2 here. So we can see there are two distinct integers. But suppose in case we pick up 2 here and here 2, then we can see there is only one distinct integer, but we want the maximum. So we will take 3 and take 2. Suppose like this, similarly we move to here, then here, like this something. Here a1 is 3 and b1 is 2. Here suppose a1 is 4 and b1 is 5. And here suppose a1 is 3 and b1 is 4. So what can happen here? We can take 3 here, then we can take 4 here. Then whatever we take, 3 or 4, there will be only two distinct numbers. So that won't work. So what we can do is we can pick up here 2, then we can pick here 5, then we can 3. So we will get the maximum. So this is the question. I hope you understood it. So what our logic is, see, either we can pick 3 or we can pick 2. So here 3 or 2 is like in a superposition state. We can pick either 3, we can pick either 2. So we can consider them as a single vertex or like a single group of vertex or something. We can pick either of them. Then we can pick, when we come here, we can pick either 4 or 5. So again, here we can pick anyone or here we can pick anyone. So cool. And what we can do is, here is 3 and 4. What 3 and 4 will do, join this. So this became a single like group of vertex, and from here we can pick any like 3 elements. So we can easily do this 2 uh, and like what we can do is 4 and 5. So we can pick like this. So our logic is basically keeping the numbers in the balls like AI and BI. We will consider these two as a vertex and we will join them, and we will see, like suppose let it be like this. Suppose here is 3, suppose here is 3 and here is again 2. So we are initially joining 3 and 2. Cool. Then again we are getting 3 and 2. When we are getting 3 and 2, this forms a cycle. So now here another thing is, when a cycle is formed, what it means, we have already used both of them. Like for the maximum we have used a 3 and 2. Like if you pick here 3, here 2, then again if 3 or 2 comes, we can't pick any. So it is another thing to mind that if cycles are presented, like if two vertices are like one edge is like occurring 2 times, basically we have already picked both the distinct numbers, and so like we can't pick them again. So let us consider a case 3 2 2 4 and 4 5. So we are picking 3 and 2, we are joining. So there is a single edge, no cycles, nothing. We can pick 3 or we can pick 2, doesn't matter. Then there is a 2 and 4 combination, so we can pick either of them or like either of them. So what we can do is pick 3 and 4, that will give us the like or what we can do is 2 and 4, doesn't matter, like no cycles, no issue. Let's not consider it as 4 5, let's consider it as 4 3. So next comes is 4 3. So here also we don't have any issue. What we can do is pick first 3. So we are not picking 2 here. So next we can here pick 2 in the second, and in the third we can pick 4. No issue. Suppose we move to another step, and here A1 is 2 and B1 is 5. Suppose not 5. Suppose A1 is 4 and like 3 and 2 are joined, 2 and 4 are joined. Suppose A1 is 4 and B1 is 3. So what we can see here is, like already this has become a cycle, and because this has become a cycle, that means we have used all the vertices. And since we have used all the vertices, we can take a new element. Basically we have used 3, we have used 2, we have used 4, because there are 3 edges. So basically 3 of the elements are used, that's why there is a cycle. So when here 4 and 3 comes, we can't use. So we are first here, so we can get 1 distinct elements, 2 distinct elements, 3 distinct elements. But here, since it has formed a cycle, 3 distinct elements. Another thing to notice is, suppose like instead of taking graph now, I hope you understood the conventions of the vertices and stuff. So suppose our 1 2 2 3 and 4 5 6 are like, we are in a state where like this is the case, and then we are moving to a vertex where AI is 3 and BI is 6. What that means is joining these two. But that thing is, what this means, this means we have already used 1, we have already used 2, we have already used 3. What this means, we have already used 4, we have already used 5, we have already used 6. So when we merge 3 and 6, because there are 2 cycles, so what will happen, we can't uh, pick a new distinct element. So that's why what we have to consider is, like what we have to make sure, is which distinct elements are joined at first, like in the same group. What we have to make sure is uh, distinct elements in the same group, and in that group we have to know that if cycle is present, So basically these two are our main things we have to keep track of. The distinct elements in the same group and its cycle is present. Suppose why distinct elements? Suppose 1 and 2 is there. Again 1 and 2 comes. So basically we have used both 1 and 2 and there is a cycle. That means we can't use any other vertex or something like that. Suppose here it is something 1 comma 2 and we move to an edge where it is 2 comma 2. So here also see 1 comma 2 is we are joining it once and 2 comma 2 is here. So here a cycle is present. In this group, there is a cycle present here, this. What this means is we have used 1 and 2 both for the maximum number of things. And so here cycle is present. So for this what we will do is basically we will keep a DSU. But the thing with DSU is since we are moving in a tree, uh, like let's consider this example only. So our input format is basically wait. Input format will be like 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be our AI and BI and this will be our tree. So let's make the tree at first. First is 9 and she is joined. Then 1 and 9 is joined. 1 and 9 is joined. Then 3 and 6 is joined. Then 4 and 1 is joined. Then 3 and 8 is joined. Then 10 and 9 is joined. Then 5 and 4 is joined. 7 and 2. Where is 7? Okay, 9 and 7 is joined. So 7 is there and 2 is there. So this is our tree and we are given the numbers also. Here it is 2, 5. Then 9 has I guess 9, 3. 2 has 2, 2. 3 has 8, 8. 4 has 4, 3. 5 has 6, 10. 7 has 8, 1. Sorry, not 7. 6 has 8, 1. 7 has 9, 10. 8 has 1, 7. 9 has 9, 3 and 10 has 5, 10. Okay. So what we will do here is we will start a DFS because here we are given like the shortest path and we know the shortest path will be given the shortest path will be just the root of the DFS because it's just in tree. So here what we will do is basically we will start our DFS from vertex 1 and here is 2 and 5. Okay, so we will keep track. What we have to keep track are the distinct elements that are in the same group and if there is a cycle present in that group or not. So two things. So at first we will move here 2 and 5. So 2 and 5 are joined. We can pick either of them, no issue. Then we move to 9. When we move to 9 we see 9 and 3, no issue. 9 and 3. Now what the thing is like 2 and 5 and 9 and 3. Okay, so basically in 2 and 5 we are merging and we are successfully merging. So here we can get 2. So let's keep a track of that also here only. So here we can at max have 2 distinct because there are 2 groups. Okay, then from 9 to 3 let's move on to 7. Okay, 7 there is 9 and 10. Okay, so 9 is already in a group and we add 10 also in a group. No cycles are present, no issue. When we add 10, yes, we can increase one more, we can take 3 distinct elements. So here it will be 3. Okay, cool. Then we will move to 2. Then we will move to 2 here. There it will be 2, 2. So 2, 2 will come here and yeah, there is now a cycle. So what the thing is, there is no issue. The cycle is coming for the first time. So now it is fixed. Then 2 and 5 in this path 2 and 5. This will be if this will be 5 without no doubt. We will take 5 here, 3 here, 9 here, and we have to take 2 here for the maximum path. So yes, our number of distinct elements will increase. No issue. Just a cycle is formed, so no issue. Then what we do is we will move back now, come here back. When we move back, what we have to do is move back in the DSU, we have to undo the steps. So we undo the step. We move back here. What vertex were connected, 9, 10 were joined in this step. So we will remove 9, 10. Okay, now we are in the vertex 9. Now instead of going here, we will now go to vertex tree. In vertex tree, wait. In vertex tree, our 8 and 8 is already joined. 8 and 8 is already joined, so we will make a vertex, and 8 and 8 is joined. So there is a cycle present now here. What means is what that means is like we have to take 8. Okay, now that's okay. So when we have to take 8, here it was 2, right? So when we have to take 8, it is compulsory to take 8. So we will move to from 2 to here. We can take at most 3 distinct elements, no issue. Then from here we will move here. Okay, so what here we will be joining is 8, 1. Okay, so what the thing is, there is already a cycle present. Okay, 8 and 1. So we will join 1. Initially 1 and 8 and 1 were not of the same group, so we can take an extra distinct element, no issue. So we will take here, it will become 4. And now we will move back. We will start undoing the operations. So 8 and 1 will be broken. Okay, then we will move this side. Here it is 1 and 7. Okay, 2 new distinct elements, no issue. 1 and 7. So we will get one more distinct element. So this will become 4, no issue. Then we will move back. So we will undo our DSU. Okay, so then we will again move back. So 8, 8 will be also removed. Then we will move to this side. In this side we come across 5 and 10. 5 and 10 will be like here. No cycles, nothing present. We can increase simply. So this will become 3. Then we will undo it. Undoing it will cause this to change. Okay, then we will move again back here. So even our 9, 3 is removed. Okay, 9, 3 is removed. And then we will move to this side. In this side, our 4 and 3 are the new elements. So 4 and 3 will be joined. And because here it was 1, here it will again become 2, because we can do 2 distinct elements. It can be any, no constraint or anything as such. And then we will move here. Here it is 6, 10. 6, 10, no issue, new vertices. So like new distinct elements, so 3. So, and then we will again simply move back and keep on undoing the things. So at last we will have like just 2, 5, and yeah, that's it. So by this movement, by this DFS, we have calculated the answers of our question along with it. So what we can see is here like 2 is 4, yeah, it matches. Like let's see if it matched or not. 2 is 4, yeah, it matches. 3 is 3, yeah, matches. 4 is 2, yeah. 5 is 3, yeah. Then 6 is 4, yeah. 7 is 3, yeah. 8 is 4, done. 9 is 2, yeah. And 10 is 3, yeah, cool. So this is our main method. There were in this question, in this example, there were some cases which were missing. Like suppose there were like cycle and another cycle, which we already discussed. Adding this edge will not lead to any new distinct elements. So that case is missing here. That we have to think as a edge case. And yeah, so for this we will use our data structure. We will use DSU only, but along with rollbacks. So this is basically a template, simple init function, then getting the parent, and we are joining by this size. So this is a union. We are keeping the like new operations here in the edge. These are the like operations we are like changing, like updates, we can say changes. And then VLLs stand for vector of long, and cycle will be like if there is a cycle present or not, simple. So like if a cycle is not present and they both belong to the same group, then there is no issue. We are getting an additional new element, but what we have to do is like we have to change that group cycle to like true, because now there is a cycle present. So in case that edge again comes, or any edge comes in that group, then it will be a false. We cannot get a new distinct element. So cool. So this is basically checking if a cycle is there or not. Suppose like here it is a cycle, and then suppose it is 1, 2 and 3. So here we again get 1 and 3, both parent will be 1 and 1, and we know in 1 there is a cycle present, so we will return false. That means no new distinct elements were found. So that is the case here. And the other case will be this one. If suppose this is this case, like 1, 2, 3, 4, 5, 6. Suppose here the parent of this group is 1 and the parent of group is 4. So here both are different, so it won't go to this if else condition. It won't go to this if else condition. So here like both have like true in the cycle, so this will directly return false because no new vertices will be found here. Then normal DSU, like we are unioning it through size, and then basically the size, normal thing, parent, and also basically suppose 8 has one cycle and we join 1, so this whole group will have now 1, will have a cycle. So for that we are keeping this also. So basically, and then like returning true because yeah, we are getting a new distinct element. And for the undo thing, what we are doing here, we are keeping the history, right? In the E we are keeping the history, so we will basically pop back like from behind, and then we will just move it back to what its state was before adding it, because here we are using a reference operator, so we like the dot first element will be like keep changing, and the dot second will keep the history. So that's how we use DSC rollbacks, and this is the DFS we will be running. So basically we will keep the initial size of the history. Basically like history is something like this. So till here we have the history, then we add something more and more. So here we know the size is 2, and then we add something here, then we move, then after this is over, then we will have to remove all this, right? So when we remove all this, we will like undo the changes. So that's why we need to keep this size thing, and then we will undo it till that size, and like this the DFS will run. And our basic this will be is like taking the A input, B input, then for the tree, then we are keeping the answer, we are directly storing the answer here. Like if there is a new distinct element, then we are adding this to the result, which is the number of distinct element it contains. Okay, so AI and BI, then U and V basically taking the 3 vertices, then we are running the DFS, and along with the DFS our answer will be stored like I showed in this like example, and then answer is stored, and that is how we will find a solution for this question. So yeah, that is all about E, F and G. Dimple, are you there?
Record off কৰ
তই হেৰিটো বুজাই দে, তোৰ ইটো বুজাবি নে, ইটো নে এফটো?
নালাগে হ'ব দে।
এই বুজাচোন, মোৰ বুজিব লাগে, মই বুজি পোৱা নাই।
স্ক্ৰীন শেয়াৰ কৰ।
মোৰটো কাটিলি ন?
स्क्रीन शेयर हो रहा है?
या
हाँ, तो एफ का स्टार्ट करते हैं। हाँ, तो when I saw the question, like, I thought I have to find the minimum step for reaching from 1 to n, not m, sorry, 1 to m, right? Yes, 1 to m. Okay, so like merging two vectors takes 1 step. So what I thought of calculating for each element, like for each digit in this vector or this vector, like what will be the minimum steps it will take to like reach that index, like to reach 2 from 1 it will take 0 steps, to reach 3 and 5 it will take 0 steps, but to reach 4 it will take one step, like we have to merge this and this. So what happens, like for this one, like let's say, um, okay, when we merge these two, like the like I, I can reach 4 by one step from one, and 7 by one step from one. Okay, this is the updated value. I can reach like what happened till now. I can reach 2 by 0 steps from one, like 0 steps. I can reach 3 and 5 by 0 steps. I can reach 4 by one step, like 2. I can reach 2 by one step, and that by merging this and this, I can reach 4 by one step, and 7 by one step, because I am merging this and this. Okay, now for this one, I can like I can check like I can reach 4 by one step. So taking another step will make me to reach this vector, and this vector includes m. So I can reach 4 by one step only, like from this and this. 6 by two steps, like from here I'll come here, and then I'll come here. Okay, I'll merge this with this and this with this. So what happened till now? Let's see. I can reach 2, 3, 5 by 0 steps, 4 and 7 by one step. How? Like I merge this and this. How? Like I checked to like how much time it took me to like it's any one of the indexes or any one of the numbers from this vector. Like I'm starting traveling from now, so I reach 2, then I can reach these factors. And for this also I have reached 4 by one step, so it will be one step only. So I can reach this factor by two steps. I can merge this with this one. I can merge this with this one, because this has a common element. So merging four this and this take one step will take. So every index of this factor will take one more step to reach from one. Okay. Now how we do this? Like I'll check like 4 has one step. 4 can be reached from one by one step. 6 can be reached from 1 by 2 step only, because I have to reach 4 and then again 6. 7 can be reached again. 7 I have reached by 1 step only, so this will be 1 only. 8 can be reached by 2 step, because I have to reach 4 or 7, then I can reach 8 after merging this and this. So that is the thing. Like I am calculating for each index how much steps it took me to reach that index, reach that number. So just looking at the implementation. Mm, mm, okay, let's look at. uh, I have sorted the factors previously. I've sorted all of the factor inputs. Then I am going through the factors. Okay. Now going to the factors. If the factor contains one, it will be at the first index, because the factors all the factors the minimum index maybe one can be AI is from one, I guess. It cannot be less than one. Then now what is this step? Okay, I am trying to calculate the minimum steps to reach any of the values. Like let's say, okay, value. Mhm, mhm. Okay, for this one, like to reach one, it will take 0 step, because I am starting from one. So what happens? I am trying to calculate for this factor. I am saying for this factor. I'm trying to look at if I can reach 2 by like some number of steps, I can reach this whole vector by merging like which vector 2 came from, like this one. If I know how much steps it took me 2, I can merge this one with that vector, and that will lead to one more step, add to each element of the this vector, new vector. So what I am doing is first calculating the minimum of like every element, like how much it took to like कितना steps लगा 2 मिलने में, 4 मिलने में या 7 मिलने में, अगर मिला तो if मतलब vector में मैप में हुआ, then because अगर पहले मिला ही नहीं मुझे 2, जैसे कि 4 में मिला ही नहीं मुझे, 7 में मिला ही नहीं, I cannot reach that. So I'm calculating if I can reach any one of the elements from like 2 from 1, then I get the minimum steps to reach that vector. Like I to reach 2, kitna steps laga, plus 1 to merge that one with this. Okay, if I cannot reach this vector by any means, or it doesn't contain n1, then I cannot reach this vector, I cannot merge it. Okay, just skipping it. Then what happens? Like I have calculated how much steps it took to reach this vector, and then I am assigning the values of this vector, like the minimum how much step it required to reach this vector. Like it took me mn steps to reach this vector, and I am updating for each element. Like for 2 I am not updating because I have reached 2 in one step only. I do not need to update that by 2 because I can reach 2 by 1 step. Why would I reach 2 by 2 step? I'll take why would I take an extra step to reach 2? Because I can reach it by 1 step only. So I am updating if that exists in the map, like if that that element is reached previously, then I am taking the minimum of current step and how much it took previously to reach that. And otherwise, if I have not reached 4 here, I have not reached 4 yet, so I am just updating by the minimum value for 7, that is 1 for this. That's all. If at last I'm checking if I can reach m, like if I have reached m by anyhow I have reached m, then answer will be the mp of m because it contains the minimum number of states to reach that number. Otherwise, the answer is -1. I am taking an extra 10 loops to just find out things better, in a better to repeat the process, because vectors can be jumbled, so it may not give the right answer at the first step. Like if there are 3 vectors like this, if there are 3 vectors like this, I can go to this vector, then I may come to this. So if I take only take one loop, what will happen is I will get here. This jump will not be happening. So for that I have taken an extra loop. So I am going and then here, yeah, calculate the minimum number of steps to reach that number. Okay, that was all. Thank you.